If you put single strands of wire wool across the terminals of a battery, it glows yellow, gets very hot and melts. What do you think would happen if we swapped out the wire wool with a large adjustable spanner like this and put it across the terminals of a much bigger battery? Don't be tempted to try this at home though. We're going to do a quick run through using some simple physics about what will happen if you do stick your spanner across the terminals of a battery. I got these dimensions for a spanner off of everyone's favourite shopping website. I'm just going to assume it's a rectangle, like this. What we're really interested to find out is how much current was going to flow through this spanner. So in order to do that, we need to know its resistance, which we can get by looking up the resistivity for steel, which gives us 7.7 times 10 to the minus 4 ohms. We can use V equals IR and a voltage of 12 volts for the battery to get the extremely high value of current of 1.6 times 10 to the 4 amps. So, quite a high current then. Next I wondered, how hot will this spanner get? Then using power is volts times current, we get the power dissipated is 190 kilowatts. Given that the specific heat capacity of steel is around 490 joules per kilogram degrees C, we can work out the value for the temperature rise in 1 second for our steel. This comes out at around 1500 degrees. The melting point of steel is about 1300 degrees centigrade. That means that this steel spanner would liquefy in around about a second. Well, we've had a lot of fun here with some physics, but let's see if we can work out what's really going on. You'd be sad to learn that in fact our spanner will not vaporise or melt, but it might get rather hot. This thought experiment is a great example of how taking some school physics and just applying it to an everyday situation can lead you up the garden path with exciting ideas that actually don't happen in real life, sadly. All cells have an internal resistance. Typically, for a car battery, this internal resistance is pretty small. I'm going to use a figure of 0.1 ohms. This in effect means we have a 0.1 ohm resistor in series with the resistance of the spanner. In turn, this means that much of the energy from the cell, or voltage we should say, is dropped across the internal resistance of the cell rather than across the spanner itself. This in turn means that the amount of energy dissipated in the spanner is an awful lot less than we calculated. The result of all this is that the actual cell itself will get pretty hot, and the spanner won't get as hot as we had previously predicted. If you found this video interesting, why not check out this one?